So it's my pleasure to introduce Otmane Sakhi and Imad Aouali, who are both, uh, Otmane was a PhD student with Nicola, who you all know, and myself, and he's recently joined research at Criteo, and so PhD at NSE, and Imad is also at NSE with Victor Emmanuel Brunel and Anna Korba. Both of them are brilliant. It's always better, a good idea to have PhD students that are smarter than yourself. So they seem to have struck gold here. And the topic, I think, slightly changed. So you're presenting, I think, around a NeurIPS paper that you've had accepted, and you'll be there in 2 weeks, something like just around 2 weeks. And this is a more general discussion of the results in that paper, and I think a lot of background. So please feel free to share and jump in. And if there are any questions, you can put them in the box and I'll pass them on.
Perfect. Thank you. Thank you for your kind words, and thank you for the invite as well. As you can see, yeah, the title changed completely from the invite. The title right now is Principled Offline A/B Testing Achievable? It's a presentation like prepared meticulously by me and with the help of Imad, of course. And the idea is to talk a little bit about the practical implications of our recent NeurIPS paper. So it's, of course, based on the logarithmic smoothing for pessimistic of policy evaluation, selection, and learning. It's a paper that was based on some results of my last PhD chapter. And yeah, it was developed with Imad, Pierre Alquier, and Nicolas Chopin, and resulted in a really good paper accepted at NeurIPS. Like really good. Even if it's my paper, I think it's really good. It's not really because it's unbiased. And the idea is simple, but like the paper itself is really full of new derivation techniques, theoretical insights, and practical results as well. And if I want to summarize like the whole purpose is that the paper gives an offline estimator of online performance with the best confidence intervals that exist in the literature. So I really invite you to go look at the paper if you're interested. But this talk in particular will focus more on the practical implication of the work, especially on A/B testing. So we'll begin by the question we were trying to answer with this talk. And the idea is, in general, like whenever we want to make a decision or a policy that takes decisions, we want to measure its effect. And A/B testing is considered the gold standard to measure these effects. So it measures the treatment effect of our decisions in many applications. And the idea behind it is simple. Imagine we have a population of like n users or patients, for example. We split this population into two. So we have like two subgroups, A and B. And to measure the effect of a treatment by A here, we compare it to a baseline. So for example, if we want to administrate new drugs, we give the population B a placebo, and population E our new treatment, and we compare the treatment effect between pi A and pi B. And to do so, we need to act with both treatments, one on the subgroup A, one on the subgroup B. And one can think, or one can say that this A/B testing, or like because it's forcing us to act with both policies. Sometimes it can be very costly. Sometimes it can be very risky, or both. So the question that we're trying to answer is, can we measure the effect of our actions before acting? Or can we measure the effect of this new treatment without even applying it on a new population? And this is translated in our language by, is principled offline A/B testing possible? So by offline, it means that we don't act with this treatment, and we do it in a way that we avoid acting with the new treatment and still have guarantees or still have a way to measure its effect. So for example, in the Rexis community or like in recommender systems in general, it can be used to measure the performance of a new recommender system before deployment or measure the efficiency of a new treatment without testing it on patients. Here I'll begin by just covering the formalism rapidly. We have a space of actions. Like to define our formalism, we need a space of actions A. Here we suppose that it's discrete. It's maybe like the drugs that we can administrate, the products that we want to recommend, or even the user interface of like certain websites. We need users and or patients, for example, depending on the application. And these are represented by features called context here, context X. And we assume that these contexts are coming from an unknown distribution and they are like independent. We have actions, we have context. So we need to know the effect of actions on context. And this effect is encoded by a reward. So this reward is linked to a context and an action. Here we suppose that it's bounded. And it's also coming from an unknown distribution. And it can model really several things like watch time, user retention, for example, in recommender systems or like patient recovery when we talk about drug administration. And then we need to model our decision system or how our actions are made. And here they're made by stochastic policies. And by these policies pi take context as an input and define distributions over the action space. And actions are made through sampling through pi. So for each context x here, conditioned on x, pi given x is a distribution over the actions. And this allows us for every context, for example, for every user, to personalize the treatment. And this personalization can be either randomized or deterministic. And here, as we said, the acting is done through sampling. So we sample an action from pi given x, and this leads to the action done, or the action that treats the context here. So a round of interaction is defined by we see a context x coming from new, we play an action from pi given x, and we receive a reward. And the goal here is to find the policy that maximizes the value or the utility, which is the expectation under, here it's the value of pi, defined as an expectation under the context coming from new, and the actions done by the policy that we want to evaluate or measure its performance. And here it's the reward coming from playing action A for the context X. And in real world scenarios, what happens is in general, we already have a policy pi 0 interacting with the environment. For example, in the recommender system use case, we already have an established recommender system that is already recommending items or videos or whatever to users. Or for example, we already have a policy that prescribes some drugs for users, for patients, sorry. And here the goal switches a little bit, shifts from identifying the best policy to, for example, find a policy that improves on pi 0. So in practice, what we're really looking for is a policy pi better than pi 0, which can be encoded by this difference, is the value of the new pi minus the value of pi 0 bigger than 0. And A/B testing answers this by building independent estimates of v of pi and v of pi 0 here. So like we have estimates, v hat of pi, v hat of pi 0, by acting independently on two subpopulations, as we said. So pi acts on population A, pi 0 acts on population B. We build some estimates of these two values. So we just by plain Monte Carlo, we get like unbiased estimates of y of pt and y of p0, v of pi 0, sorry. And this difference here, so the difference of the two estimates quantifies the improvement. Of course, these estimates are like still noisy, let's say. They have like some uncertainty in them, but the idea is we always want to be sure of the improvement. So we can use confidence intervals and, for example, just leverage central limit theorem to have these lower bounds on this difference of the value. And we can say that we would be confident with 1 minus delta certainty when the difference of the estimates minus an uncertainty term here based on the empirical variance divided by the number of observations is bigger than 0. But as we said before, we need in this like online A/B testing or in normal A/B testing for pi to act on population A. Pi can be bad. Sometimes it can lead to catastrophic outcomes, especially when like we want to try, for example, new treatments. It can be costly, especially if you want to test multiple policies. So imagine we have like a big candidate, like a big number of candidates, not only one candidate that we want to test. And the question is there a cheaper way to answer this question confidently? Or can we confidently answer this question without pi acting in the environment? And this is what we will try to answer in the next slides. Here we introduce what we call the pessimistic of policy selection. And let's say that we have a set of policy candidates, pi 0 till pi k. And of course, like when k is equal to 1, we end up by pi 0 and pi 1, which is the A/B test setting. And the goal, as we said, is to find a policy from this policy set that maximizes the value. So we look for pi star, which is the argmax within this policy set of the value. So we'll want to look for the policy here that maximizes the value. The question is, how can we answer this without any pi acting, interacting, like acting or interacting with the environment? This is super hard. But what we can say is that at least we know that we have a policy pi 0 already interacting with the environment. So we can leverage this data, or we can leverage this knowledge to evaluate all of the other policies. So if we have one policy within this policy set interacting, maybe we can do it. And how we will do it is we leverage all of the previous interactions of pi 0. So we build a data set here of the context, all of the contexts seen, all of the actions done by pi 0, and all of the rewards collected. And in our paper, we define the logarithmic smoothing estimator, LS, of this true value here by the following formula, which is an empirical average of a transform of the importance weights multiplied by the reward. So if lambda is equal to 0, you will get the IPS, the well-known IPS estimator, the importance weighting estimator. And with lambda bigger than 0, you logarithmically smooth big importance weights. And you can see here from the graph. So the blue line is IPS. There is no smoothing or clipping. If you're familiar a little bit with other estimators, there is an estimator that clips big importance weights to mitigate the problem of variance. And it looks like this. So for all of the importance weights that are smaller, for example, than 20 here, its value is of IPS, but once you go up, like if you exceed 20, you're clipped there. And you can see that logarithmic smoothing here corrects these weights logarithmically, and it has like a nice properties of being differentiable. And as we can see afterwards, it has also like some really good concentration properties. So once we define that estimator, we can give a lower bound on the true value of any policy coming from this policy set here with high confidence. So for any policy here, we can get, or we can prove that this lower bound or this inequality will hold with confidence at least 1 minus delta. And it will give you a way to lower bound something. So it's a quantity that is untractable. So it's a quantity based on some unknown distributions here, lower bounded by quantities that you can compute directly from the data. And we prove in the paper that it's the tightest finite sample lower bound that you can get in the literature for now. And we leverage this result to obtain really good ways to select policies. So instead, because as we said, we want to identify the argmax of the value of pi k, this is not accessible, but what is accessible is a lower bound of a holding with high probability. So instead of looking for the argmax of this, we look for the argmax of the lower bound. So we get pi n, which is the argmax of this lower bound, boiling down just to the argmax of v hat, because this term here does not depend on pi. And the question will be, okay, now we get a policy coming from our empirical estimator of the value. How can we know that the policy obtained matches pi star? What we can know is with properly chosen lambda, so a lambda here that decays in square root of 1 over n, we know that the value of pi star minus the value of the chosen policy, of course, it's always bigger than 0 because this is the optimal policy, so it's the argmax, so this difference is always bigger than 0, but it's bounded by something that decays, something that goes to 0 or that decays with n. So we're pretty happy to get this result, telling us that with enough data, pi n will converge to pi star, or its value will be really close to the one of pi star. And what is good is we also know that if pi star is really close to pi 0, this convergence will be super fast. So this convergence, of course, depends on the number of data, but will also depend on how close the optimal policy is to the policy that is already in production. So this is the result that we can have from building or looking for pi n. But this does not really tell us if we improve on pi 0 or not. It only tells us if we're close to pi star, but we don't know if any of these candidates here is better than pi 0. So this is why we will frame the problem a little bit differently, and you will see that we will get maybe an answer to our question. So instead of framing it as a selection problem, we will frame it as an improvement problem. And it's really easy to see because there is like a connection between the two. Looking for the argmax of V can be seen as looking for the argmax of the value of pi k minus the value of pi 0, because this does not change anything. And we can just frame the question differently and ask, is there any policy for which this difference is bigger than 0? And we do the same logic, or we use the same logic as we had before. So just instead of focusing on the value of pi, we focus on the difference of values. And instead of defining an estimator of the value, we define an estimator of the difference. So we define here the logarithmic smooth difference, which is an empirical estimator of the difference of the value of pi k and the value of pi 0. And using the same tools, so these results do not figure in the paper, but one can derive them directly with the tools that we have, that for any pi k, we can be confident of the following lower bound, which is the value or the difference of these values, v of pi k minus v of pi 0, is always bigger than this ls, the logarithmic smoothed difference, minus like an uncertainty term here. And you can see that this is purely empirical and that it can be computed directly from the data that was previously collected by pi 0. So how can we be sure that we improve on pi 0? We just look at this empirical lower bound and see if it's bigger than 0 or not. So it transforms the problem of looking for the argmax to just look at the difference minus uncertainty term. If it's bigger than 0, you are sure with confidence 1 minus delta that one of the policies in your candidate set is better than pi 0. This result depends on lambda here. So we choose a lambda that will maximize this lower bound so that we have a better chance for it to be bigger than 0. We choose this lambda, which is based on the second moment here of the difference. We can see that it involves the importance weights minus 1 multiplied by the reward squared. And once it's plugged in, you have criteria, which is based on an empirical difference. This is an estimator of the difference of the value of pi and pi 0, minus an uncertainty term that has an empirical variance or an empirical circuit moment in it. So it really looks like the A/B test criteria that we had, just that we had online. And now we have something similar to it offline, and that holds for finite sample and with high confidence. So let's compare the two. And here we only focus on the A/B test scenario for ease of exposition. So the candidate set here is like it has only pi 0 and pi, and we fix here a delta, which is the uncertainty level, as we've seen before. In the online setting, what we do, we have pi act on a population A, pi 0 acts on population B. Of course, these two populations are independent. We build these two estimates, and we use CLT to define our selection selection criteria here. Offline, what we do is we only let pi 0 interact. We leverage this data collected here and compute the empirical difference, the logarithmic smoothed empirical difference here. And we define our selection criteria by just the empirical difference minus square root of uncertainty term multiplied by the empirical second moment. And let's suppose here that these two differences are of the same order and that our uncertainty level is set at 0.1. With these uncertainty levels, we just evaluate here the z-score of the Gaussian, like the CLT, and here it's square root of log 1 over delta. And you can see that both are comparable. Because here we need, in the online setting, we need to split the population. We set NA equal to NB equal to N divided by 2, just for a fair comparison between online and offline. Because in the online setting, we split the population. In the offline setting, pi0 interacts with the whole, let's say, population. So you don't really need to split anything online. So with this, you have here the for the online setting, you have square root of 4 sigma squared divided by n. For the offline, sigma squared square root of sigma squared 0 divided by 2n. So if we want to compare the two, we have in the online setting a variance or a second moment close to 4 of the second moment of the reward. And offline, what we have is 1 over 2 second moment of r multiplied by this difference here. So you can understand, or you can just like by comparing these two, you can see that like online should be better when pi is very different from pi 0. Because once pi is very different from pi 0, W, so the importance weight, will deviate a lot from 1. So here you will have this second moment much bigger than the second moment that you have online. And in the other hand, the offline approach will be better when pi is close to pi 0. So when these importance weights will not deviate a lot from 1, you will get this second moment here much smaller than the online counterpart. And why is that? It's because in the online setting, the fact that we need to split the population into two, even in an AA test, an AA test means that pi 0 is equal to pi, like both policies are the same, you still need to suffer the variance coming from the reward. And in offline, because you use the same data for both, once pi is equal to pi 0, the variance pi equal to pi 0, it will give you like an importance weight close to 1. So this variance will shrink, and the results that you get offline will be much more confident compared to what you get online. We want to validate also these things in a simple problem. So we define here a scenario with an action space of 10 actions. You can think about it as like a website for which we want to test different layouts. So each action here can be a different layout. And we also think about a scenario where we have a small treatment effect. For example, like layout number 1 results in a click-through rate of 0.01, and layout number 10, which is the best layout, its click-through rate is still very small, but what is good is that its relative improvement is 3%, which is actually really good in recommender system community, or like in the like online in general. And as the difference here, for example, from the best action to the least good action is of order 10 to the power minus 4, because here, if you see this absolute difference, you get like 3 to 10 to the power of minus 4. We need at least n bigger than 1 million, which is acceptable online, let's say. So we start all of our tests with n equal to 1 million, and then we can increase it. And in the next slides, we can see that we will test different configurations of pi 0 and pi for different n's, and we can compare offline and online for each configuration. For the first one, for example, pi 0 and pi are not that different. Pi is just, let's say, a deterministic version of pi 0. And if you look at this difference here, so how the importance weights deviates from 1, you can see that it's quite small, so it's 0.44. And what you get is deploying both online, so doing an online A/B test will only capture the improvement starting from 50 million samples. As if we compare it to the offline setting will capture the improvement starting from 10 million interactions. So here in this particular example, we see that the offline approach that we developed can be better than the online A/B test. If we change the configuration a little bit, so pi 0 is putting a lot of mass on the first action and explores all of the other actions. And pi here does some, yeah, just selects different actions than pi 0. You can see that here the deviation becomes a little bit bigger. So we went from 0.44, sorry, to 4.36. And if we look at what we can capture offline and online with our methods, like this is the online A/B test, you can see that the improvements can be captured starting from 10 million interactions. And offline, you can capture the same improvement starting from 10 million. So both are comparable. We go to a much harder case where pi 0 and pi are substantially different, but we still have pi 0 exploring a little bit in action 4, while pi puts all of its mass on action 4. You can see that the deviation becomes even bigger. And here, because the online approach does not care about how pi and pi 0 are related or how close or how far they are, you still get the online approach that like capturing the improvement, sorry, from 10 million interactions. In the offline part, however, because the deviation is really big, so pi is really different than pi 0, we only start capturing the improvement starting for 500 million interactions, which is really big. And of course, I'll give the last example, which is pi 0 pretty much does not touch this action here, so it doesn't really put a lot of mass on the action 4, while pi only swears by action 4. And you can still see that online, of course, is independent of the, let's say, the distance between pi 0 and pi, as offline will suffer a lot because this deviation is really big. So you don't really capture any improvement maybe at 1 billion interactions. Like starting from 1 billion interactions, maybe you can see it capturing something, but before, all of the lower bounds here are really, really small, like really far from 0 here. So we come back to our question, like the question that we asked ourselves at the beginning, maybe, yeah, it was the title of the presentation, which is principled offline A/B testing achievable? And from this presentation, we can see that the answer is yes, but under a lot of conditions. And what is really good is that it can be even better, like offline can be really better than online if we evaluate policies close to the production policy, for example, or the policy that is already collecting data. The results are coming from our NeurIPS paper, and we don't have proofs for them in the paper, but the proofs are left as an exercise if you want to. And yeah, you can see that this presentation is more like an invitation for people to really look at the paper we have with Imad, Pierre, and Nicolas. It's really full of new derivation techniques and new like insights. So yeah, feel free to look at the paper, maybe talk to us at NeurIPS at Paris, talk to us at NeurIPS, send us an email. I'll be really happy to discuss. Yeah, thank you. That was it.
Oh, thank you. That was really nice. And if anyone else wants to ask a question, I can either turn on your microphone or you can put it into the box. I can't let pass that you're claiming you can be that an offline can be better than an online. What does it? Firstly, but I really like that the example has like really small treatment effects, which you don't see so often in these papers. But how's that possible? Like that feels like there's maybe it's worth running back to the
Yes,
slides when you make this claim. Like,
that's true.
I had the same question, and I think you will be convinced. But
sorry,
I had the same question
yeah.
because it's always surprising to see online being beaten by offline.
Yeah.
I think it makes sense once Otmane explains it.
So yeah, thank you, David, for the kind words. I tried my best for these empirical results to be as close as production as possible. So the whole point or the whole idea is that in A/B tests, especially in the contextual bandit setting, you need to split your population, right? Like if I
Right.
look back here, you need to split your population. So once you split the population, if we look at CLT, you have like this difference because you build an estimate of v hat of pi and v hat of pi 0 independently. So both these estimates are independent, and the difference, if you take a difference, this difference will suffer twice the variance, or its variance will be variance of the first estimate plus the variance of the second estimate.
So if pi and pi 0 do the same thing in some
Yes.
places, and you don't, but you just don't, if you ignore that naively use this estimator, yeah, you'll pay a cost. I agree.
Yes, so like you pay the cost even in AA test. So even if you know that pi is equal to pi 0 exactly, and you do an AA test, you will suffer the variance of splitting and the variance of the reward itself. But if you look at how our estimator is built here, if pi is equal to pi 0, this difference is directly 0. So it's because we use the same data that was collected by pi 0. So if pi and pi 0 have the same actions played for the same contexts, you will always get a 0 here. So your method will converge much faster offline than online.
Okay.
Yeah, this is the nuance between them, and that's why like I really wanted to hear like just assume that everything is equal everywhere and just compare the variances. So you get 4 times the variance of R here, and here like half the variance of R, but multiplied by this deviation term. And if this deviation term is small, you get easily offline better than online. And this is what we see actually here. Like once this deviation is small, it is easy, like the improvement is easily captured offline than online. And once it gets bigger,
Well, you have double the data. Like effectively, that's the story, right? You have double the data.
not necessarily, like you have double the data, and also another term here, which is W minus 1. Here, like this does not take into account how pi and pi 0 are different. Here it takes into account how they're different. So in the A/B test, you build estimates and then you take the difference. In our approach, we take the estimate of the difference directly. And this is what makes the offline better than online, because you look at the difference directly on the data. And this difference is computed on the data itself. And you don't need independent samples for it to be computed.
Okay.
And what was the value of lambda?
The value of lambda is this.
Because in this comparison, you take into account the variance, but there is a bias that exists in the offline setting but doesn't exist in the online setting.
What do you mean by the bias? Sorry.
The estimator of the difference is biased
Yeah.
because of lambda, right?
Yes. So it's a little bit pessimistic, yes.
But it's not in online A/B testing. So
No.
this is a source of, so the variance is high, so this is a source that it's in favor of offline, but the bias is high, so this is a source that is in favor of online.
Yes. But that's why here, for example, I assumed. So like once pi and pi zero are really close, like if we come back here and look at the logarithmic smoothing estimator. I'm sorry. Like if pi and pi zero are close, we're
So
in
that's
this region here. So the bias is really small.
so this is what I was referring to, kind of, because
Yes.
it could be related to the variance or the
True.
bias, because
True,
there are
true.
two things that are the bias is kind of hidden in all of this.
Yes, but to really ease the comparison, I just said that these differences, let's say that they're the same. Let's look at the variances. In the variance, you can see that when pi and pi zero are close, the bias is also close to zero, and the variance is small as well. So
Yeah.
you get the benefit of both when pi and pi zero are close.
Cool.
I'm just thinking if trying to maybe think of a possible way it could be used. So if you say like pi zero and pi, they're both deterministic.
Okay, no, we're going really far. So
But sometimes they could agree with each other, so there can be still an overlap. So let's say it's a real A/B test, pi zero and pi exit. But I think you could just do something very simple. It was like when you're computing the difference, just ignore all contexts and filter them out when you have the same decision. Just remove them.
like here we're talking about um here we're talking about what? Like we're talking about offline, right?
What I'm trying to say is, well, let's do it online. But if you can beat online, you can also use it online, right? You can use the offline estimator online.
Yes.
But
Yeah.
what you're really doing, I think, is identifying patches where the two methods do the same thing and discarding them really.
Yes.
That's, I think, where the advantage comes from.
Yes, the advantage comes like partially from that for sure. Because like once you do it online, like once you want to split the population and have pi acting on a subgroup, pi zero acting on another subgroup, contexts are by definition independent because we're in the contextual
Yeah.
and the framework. So you can't really say that both are the same, so I will cancel out.
What do you mean? What I'm saying is, for some contexts,
Mm-hmm.
they have exactly the same distribute. Let's just say they're both deterministic and do the same action.
Yes,
You can just discard those ones,
that is true. That is true.
and I think you get the same kind of result. In practice, in real systems, they may well be deterministic rather than.
Okay. Yes. Like
I think
I
it's a similar, like you should. Could doing something like this give you if you were online, give the benefits of the offline estimator that's even better than the online.
I still think that you get other benefits offline. So like in the case that we're talking about, imagine that we're trying two different systems and we only changed one component. So like for all of the other components in the system, they're similar. But like the one
There's only
component,
one context where the action differs.
yes. So you can look directly into those contexts. In that context, like in one context, you can, because you need to split, you need to do an A/B test on that context itself. Every action is independent than the other. So you need to estimate the value of pi and the value of pi zero, even if it's the same context. You need to, within that context, split and have them both independent. You do you agree or not?
I'm not sure I follow.
So imagine,
I mean, I think you can if they only if A and B only differ on one context. As far as I'm concerned, you could just filter out all other contexts because they're always doing that. They're always going to do the same thing on them. So you know the difference on all other places is zero, and you could just do the analysis on that context that you're
okay,
the subset of context you're interested in, and I think you will get less variance from doing that.
yes, for sure. Because I was thinking more about like continuous context, for example, like in your case.
Yeah, so I
Yeah,
think you have to
yeah,
do something more careful, and I guess that's what your method works when the two policies are probabilistic and there's some overlap. It extends what it, but I think it's the same
yeah,
argument
yeah,
actually.
it's the same idea. That's true. Like
Yeah.
once you have them matching on some context and like yeah, you can just cancel out the variance there. That is the idea.
I also wonder the fact that it works better than online when pi is close to pi zero. I wonder if using a direct method, because in that case, there is no kind of shift, distribution shift. This is what makes people not use direct method. So just learn a reward and the bias won't be that bad. And I wonder if we do that, do we get?
Uh, I think like you have two kind of biases with the direct method. You have a bias or maybe a variance coming from the collection, so the login policy.
Mhm.
But the bias that you think or like that you suffer from is a bias coming from the misspecification.
Yeah, but this in practice is using like a neural network or something. Might do the job. I don't
It's
know.
like I think like prod people, like practitioners will beg to differ with you because it's even with neural networks or like XGBoost or like all of these gradient boosting techniques, and we're still not able to model the reward perfectly.
We're now kind of talking
But,
about
but,
mechanics.
but I'm wondering if it won't be the case when pi is very close to pi zero. Because
Ah,
the reward is maybe is modeled not perfectly just in the areas different from pi zero. In the areas where we have the
yes.
for the actions that we have in log data, it it might be good. And when you do the offline thing, you get good results for pi for policies that are close to the logging policy to pi zero.
Maybe we should like look at that.
Yeah, because when I looked at the figures, I was wondering at first, oh, it would have been great if we have like other methods other than LS and see
Ah, yeah,
how they act. Do they have the same behavior, how they act? But
that is
then
true.
now that I'm thinking about it, I think even direct methods should be might.
I mean, so like your question is pi zero. We deployed pi zero, for example. Like imagine it's a recommender system. Pi zero is deployed. It collected some data. We have an empirical estimate of like v hat of pi
Mhm.
zero. let's build the reward model and see if with that reward model, it's really close to what we observe empirically. So
I'm just saying, let's build a reward model and let's take a policy that is close to pi zero.
imagine it's pi zero. Yeah, this is like imagine.
Yeah, okay,
Yeah.
perfect. So can we regenerate data from the reward model, basically? Can we? Or yeah.
Yeah, I think it will depend on the difficulty of the problem. This is always like the problem or the fear of the reward model is that it will
Yeah,
depend
but it's
on the
used in
difficulty of
LLM.
the
So
problem. Here, what is really good about these approaches is that you just don't talk about the problem itself. You talk about what you can control, and what you can control are the policies, because the problem itself you really can't control it, like it's coming from the environment. But pi and pi zero are things that you have control of. So you can easily, like if I give a practitioner um, an advice on how to design pi or how to design pi zero, or like how to do like offline tests with these two on things that they can control, it's easier to sell than tell them, oh, if you have a really perfect reward model and everything, you can completely
It's,
um,
do you want me to push back? You're inviting me to push back now.
yeah, David, you're in
I
a
mean, reward models are used in LLMs. We are using LLMs every day.
Yeah, I'm not sure if it's a reward
Becoming a big
model.
fan of reward models.
I could actually like push back, but also say sort of one point where I think these methods are useful. A lot of the problems, like when you're talking about bias, you're talking about an expectation under X, and that's really hard to do. But
Yes.
it's not necessary, because all you need to do is know the best action for an X. Now, people that like IPS or policy of these estimators, they always say the direct method has to do something that's sort of unnecessary. You need to estimate the reward everywhere, and even if you get it wrong in one place and you get it wrong high, then you can have bad outcomes. But I think it's equally true that the OPE people are doing an integral under X that you don't really need to do. Like you don't need to know the expected reward to know the best decision for any X. There's one place where what I'm saying starts to become less true, and it's if it's not a contextual bandit, but rather you get many opportunities to personalize. So you see something, you do something, you see something, you do something. Once there's a sequence like this, you can't then avoid the integral under the context. You can
Yes.
avoid the first one, but the rest you can't avoid. And that really is actually one of the main places we try to use these estimators in practice. And in Otmane, in fact, you have used the estimator in the practice in exactly that scenario. And it's exactly the scenario where it's hardest to use a model, because you now have no choice but to integrate or to build models under the context, which is really nasty. So sometimes I kind of recently came to the conclusion that these estimators are most interesting in the case where they're not really studied so much, which is when there are multiple opportunities to personalize. I don't have a good term for it, but maybe that's the best term for it. Multiple personalization opportunities rather than just one, because with just one, the direct method is actually adequate.
I think they're just here as a complementary approach to the direct method. Like it's just a way to approach the problem on things you can control, and if you target the expectation, for example, as a measure of performance. Like once you want to understand the more like the world better, or like you want to dig deeper into what is the best action for each context, I think like these methods will come, like will not be adapt. Yeah, it will not be adapted to your approach, and maybe like a direct method that looks at the context and the action independently of this integral over all of the actions over all of these contexts will be better.
Yeah, maybe, but also equally that it really have practiced that multiple opportunities to personalize. I'm going to trademark that term. I think it's the right term. That is actually a place where the OP also they'll have variance problems because it's a hard situation, but it's a situation that's also very, very difficult for a model to perform.
And yes, like I think it's even more difficult. We tried some problems. Yeah.
I mean, I can make. I think I'm repeating some various arguments about let's say the Bayesian view of these estimators, which some of these estimators, by the way, are famously bad in the Bayesian community. If you want to compute a marginal likelihood with a harmonic mean, it's classically like, do not do this, and it's an example of an importance sampling estimator. So that they're kind of classically bad, but the standard argument is that they use information that you don't need and that is not relevant, and they ignore information that is. So the propensity score is not really relevant, but the action and the context that you're seeing is relevant. So that's the kind of critical argument. There's other things like probably the X splits into two things. One thing which is something that if you like, there are two things that will impact you. One thing is it will impact the reward. So in your formulas, you have, it's not the formula right here, but you have reward given A comma X. And you also have pi A given X. Now, if X contains both something like how big the ad is and what the user is interested in, then how big the ad is likely part of the reward given A comma X, but it makes no sense to include it in pi A given X.
Yes, yeah, I get it.
Many things like this can be incorporated in a fairly natural way with models. I agree. I have no good answers to if we have to integrate under X, then you have no choice but to build a model of X, and that's really, really nasty. For the contextual boundary, we don't need to, unless we're constrained. But for multiple actions, yes, then it's really, really hard.
True. I mean, like you can always try to bridge between the two, like with like the meta policy approach or the
So you're going to go doubly robust, but yes. Yeah, true. Are there any more questions? Anything else you want to talk about? Anything you're excited about NeurIPS for?
yeah, it's gonna be our my second time going to NeurIPS, like because the first time was like 2 years ago at New Orleans. And it was one of the best conferences I went to, so I'm really excited to go. Next week, I'll meet with a lot of like French researchers at NeurIPS at Paris. Imad will be there. Like actually, Imad will be presenting.
Yeah, I will be presenting.
Yeah.
Okay, the same slides or?
Maybe a mix of the two.
Mix some changes a little bit.
They probably want more theoretical stuff. They're French.
And I'm giving them less theoretical stuff.
Oh, really? Oh, really? Okay.
And
yeah,
Nicola will be there as well. So I'm happy
that's cool.
to see him in an academic environment.
And maybe meet him for the first time.
Yeah, that'd be cool too.
For me, yeah.
Actually, I would like to. I suppose I can't go. Its registration's closed, hasn't it?
Yeah, sad for you.
But we also have a lot of stuff on at Criteo next week.
That is true.
Yeah.
Okay, well, thanks again and congratulations again. And
Thank you, David.
yeah, cool.
You.
I'll
Thanks, Otmane,
I'll end the session.
live in the
Thanks, everyone. Bye.
Thank you. Cheers.